Hello, everyone. Welcome back. Today, we're going to talk about logarithmic functions and what they are and how they're related to exponential functions. So our goals are to understand how that first fact, understand how a logarithmic function is, how it's related to an exponential function, how they both give us the same information. Understand the properties of a logarithmic function. As we'll see, they're also related to what we saw with an exponential function. Be able to use what are called the natural logarithmic function and the logarithmic function of base 10. These are the most common ones. These are the ones we found on your calculators. Also be able to graph the logarithmic functions and evaluate them. So first off, let's take a look on the left below. So a logarithmic function, we'll start with just a general base, what's called a base A, just like an exponential function had a base. We're gonna have a base with a logarithmic function, the base A, where A, like with an exponential function, A is positive and it's not 1, is written like this: y equals log, is read log base A, or y is a logarithm with base A of x. You just say log base A of x. Now, what this next statement is a mathematical statement. Y equals log base A of x if and only if x equals a to the y. Now, the mathematical if and only if just means that basically both those things give us the same information, two ways of saying the same thing. So if this is true, the exponential is true, this is true. If this log statement is true, then this exponential is true. And also, once again, this means y is the exponent of such a type, we should say, I guess, a needed base. So y is the exponent of some needed base so that a to the y becomes x. Okay. Now, let's go and talk about the properties. We'll go through some of the ideas first, then we'll actually come over to the right and actually look at some examples. So the properties of a logarithmic function, so we're going to call this f of x equals log base A of x. Once again, for a greater than 0 and a not equal to 1. And as it says, these functions, logarithmic function and its corresponding exponential function, are inverses of each other. So if you've seen mathematical inverse of each other, you understand those properties. The domain of a logarithmic function is 0 to infinity, and the range is all real numbers. And if you remember from inverses, that you switch your domains and ranges. So if you remember an exponential function, its domain was all real numbers and its range was 0 to infinity. The x-intercept of the graph is 1. There's no y-intercept. The y-axis, or x equals 0, is a vertical asymptote of the graph of f. And also that's true because our domain is from 0 to infinity, not including 0. We can never take the log of 0 or a negative number. You can always try that on your calculator to see what happens. You'll get some kind of error message or something like that. You may even say undefined. So once again, the y-axis is a vertical asymptote of the graph of f. And then a logarithmic function is decreasing if this a is between 0, if a is between 0 and 1, and it's increasing if a is greater than 1. The graph also contains these 3 points, and it says the graph is smooth and continuous with no corners or gaps. Now, before we go further, let's take a quick look here at two of the most common logarithmic functions. First one's called the natural logarithmic function, or the logarithmic function with base e. So you may have seen base e before in discussion of exponential functions. So e is a number, it's an irrational number, but it's approximately 2.718. And we write that a certain way. We call it, instead of writing it log base e like this, we call it ln for natural log. And once again, this is true if and only if x is equal to e to the y. And then a logarithmic function of base 10, we also give it a special name. We just call it log, or log. And that's true if and only if x is equal to 10 to the y. And these are, once again, the most common ones. Now, this is something that won't be covered in this particular video, but you can always get other log bases like log base 2, log base 7, and so forth from something called a change of base formula, where you can actually convert those to either natural log or log base 10. So let's come over to the right and actually look at some graphs, look at some ideas. So first, let's graph a logarithmic function. Probably graph both of these. Let's graph. Let's do y equals let's do log base 10, which is of x, of x, which is also just usually just called log or log of x. So for that, I'm going to use a grid. And also to graph this, we're going to get some help from the exponential function itself, because they're inverse of each other, so we can see where this function comes from this way. So first off, let's do the let's graph. I'm going to graph in red y equals 10 to the x. Okay, so first, I'm going to graph y equals 10 to the x, and that's going to help us. So all exponential functions have a y-intercept of 0, 1. You also have the point 1. If I plug in 1, of course, you plug in 0 for x, you get 1. If I plug in 1 for x, you get 10. So way up here. And then also, if I plug in negative 1, I will get 1/10. So that's way down here, almost on the x-axis. So negative 1 and 1/10. So this is also going to be a horizontal asymptote at 0, and it's going to look like, I kind of missed it, but you get the idea. Okay, right. So that's what that graph looks like. And once again, we have a horizontal asymptote at y equals 0. Now, the idea of an inverse function is the inverse function we can is a reflection across the line y equals x. Let me actually make that in a dotted line. So I want to try to graph that well. This line I'm trying to graph right here is the line y equals x. And for an inverse, do an inverse across this line. What you do is essentially you flip it over this line. And so what that also does, and I'll do this in a blue color. This is going to be the graph of y equals log or log of x, is our coordinate points change or reverse their x and y. So 0, 1, this point goes to 1, 0. Okay. This point that was 1, 10 now goes to 10, 1. And this point that was at negative 1, 1/10 goes to 1/10 and negative 1. So about right here. And so this graph then is going to be the mirror image of the red graph across this line. If I can draw it well. It is increasing, although I'm pretty flat, it is an increasing graph. Okay. And here we have a vertical asymptote. Let's abbreviate that at x equals 0 or on the y-axis. Okay, so these two graphs, these are inverses of each other. Okay, and also this is basically what it looks like. All right, so it is an increasing graph, but it increases very slowly. All right, so this exponential graph increases very rapidly, or an x is positive, this increases very slowly. And once again, here, as you can see, our domain for x for a logarithmic function, it is asymptote at 0. So remember, a graph never crosses a vertical asymptote, so it can get as close to 0 as you want whenever actually reaching 0. So if you do the log of some number very close to 0, you'll get closer and closer to negative infinity. And then, of course, it goes to infinity. And then also our range is all real numbers. You go as far down as you want, and also as up high as high as you want by increasing x. And so then the graph of y equals e to the x will look very similar, except we'll just replace it with, instead of base 10, with base e. It will look basically the same. Now, one more thing. This is something we don't. Let's do another graph. This time, let's actually graph y equal, let's do base 2. So log base 2 of x. And so once again, let me insert a grid below. Let's graph this. I'm also going to graph I'll say and graph this and graph y equals log of base 1/2 x. And we'll see this is actually a reflection. Now, you understand our properties to understand instead of graphing, we could use, and this is the way we just did, we could graph y equals 2 to the x and then do the inverse. But this time, let's actually understand about the properties of a logarithmic graph to graph this first. So in red, I'm going to graph y equals 2 to the x, or y equals log base 2x. Okay. So it says the graph contains 33 points, 1, 0, the x-intercept. It also contains a, which our base is a, 1, so 2, 1. And then it also contains 1 over a, so 1/2, and -1. So about right here. And so this graph is going to look like same shape as the one we just showed you a moment ago. Base 10 has exactly the same shape and it's an increasing function, but it increases slowly. It looks like that. Okay. Now, what happens then if we have a function that's decreasing? Okay, so let's think about this. It also may help to go back and think about this is something we'll also practice with, being able to write these in different forms. Okay, so this, I'm going to write these arrows back and forth. This is our mathematical way of saying this is the same thing. Let's use this property here we just mentioned. All right, so if y is log base 2 of x, then what that also means is that this is the same as, or gives the same information as f of x is equal to 2 to the x. Okay, then this in the same way gives the same information as f of x is equal to base of 1/2 the x. Okay, so we think about this. Remember this graph, if you understand exponential graphs, this is also the same as 2 to the negative x. So that was actually a decreasing function, exponential function like that. Okay, so what's this going to be? Well, this is going to look like, let's see. So this is going to be a reflection around the x-axis or the y-axis. Okay, and I'm trying to decide right now, maybe I should make this a different kind of, slightly different kind of graph. In fact, give me just a moment to decide which is the best way to write this. Okay, so what this graph is going to look like is essentially a reflection across the x-axis. Let's do this in blue. Okay, actually this point right here is going to stay the same. It's going to stay where it is. That point's going to be 1, 0. And essentially our other points will kind of flip. And so reflection across the x-axis, and this point here will now be 2, -1. And this point right here, the x-coordinates or the y-coordinates will flip. And this point, this is 1/2 1 will become 1/2 +1. Okay, this graph will look like this. Well, should go, erase that. Try that again. It should go through those points. So then what's going to be the vertical axis, the y-axis being asymptote, and it should look like a mirror image or reflection across the line of y equals x. And this in the blue would be the graph of y equals log of 1/2 x. Okay, they don't usually encounter those as much in practice, but it is important to understand that. Okay, now let's take a look at a few other ideas, especially go back to this understanding of being able to go back and forth between these two forms here. So let's say first we want to rewrite, our directions would be to rewrite as a logarithmic expression. I'll abbreviate that. And what I mean by that is we're going to start with something as a exponential expression, be able to rewrite it as a logarithmic expression. So let's start with something basic. How about 2 squared equals 4? Okay, that's an exponential expression. So what I'm saying is that's the same as this right here. So these two things give us the same information. So if we write that as a logarithmic expression, let's take a look what we have. So our base, which is 2, that's the base of our log, okay? And our y, what it's equal to is our exponent. So our exponent is 2, and then that's going to be the log base 2, and then basically your x, what the exponential expression is equal to this. So just kind of match up what we have. So our base, whatever our base is, our exponential expression always goes here with the base. The exponent is what the log is equal to, and then what's left is the 4. Okay, we'll try another one of those, maybe a couple of those. How do we do this? 10 to the negative 2 is equal to 1 over 100. Okay, well, that's true. Hope you recognize that. So if we do this in the same way, so we have our log of our base. So our base is 10. So that's always what our log. Here we just use log. That's the same as log base 10. Now our exponent is what the log is equal to. So that's negative 2. And then what's left then is just what's on this side of the exponent goes here. Is take the log of that. That's going to be 1 over 100. Okay. Or if you have a more general expression, let's say I have b to the x is equal to m. In this case, we essentially have an equation. If I just want to rewrite that in logarithmic form, okay, then once again, the same way. So my log is the base of whatever, it's a log base, whatever my exponential base is, which is b. The exponent is what the log is equal to. And then my what's left, oops, sorry, I got that in the wrong place. My exponent is what the log is equal to, which is x. And then what's left is m. And if I know m and b, then of course I can find x. Well, and the way to do that is the base, if you're going from an exponential expression to a logarithmic expression, the base is you're taking the log of that base. The exponent is always what the log is equal to, and then finally plug in the m. Now, let's do a couple examples where we're also going the other way. So we want to rewrite as an exponential expression. This time I want to go the other way. Let's take a look at a few of these. So number 1, let's say we have this. So log base 2 of 32 is equal to 5. Okay, now here, once again, we're not solving for anything because there's no x, there's no variable here. This is just a statement of something that's true. We want to be able to rewrite it in an exponential form. Okay, so once again, the same way whatever our base is, this is log base 2. So that's going to be the base of our exponential expression. Put an equal sign here. Then remember the log we said is equal to a logarithm is equal to an exponent. So the exponent, what the log is equal to, will be right here. Just match things up. And then what's left is the 32. And then you can check, make sure that's true. 2 to the 5th is 32. Okay, let's do another one. How about this one? Natural log of 1 is equal to 0. Okay, so this is natural log is log base e. So the same thing. So remember, this we have to think about. Remember to get used to this. This is log base e. So being true, then our base is going to be e. The log is what the log is equal to is an exponent. So 0 goes there, then what's left goes right here. And once again, if you remember your rules of exponents, this is true. Anything with 0 power, except maybe 0 itself, is 1. Let's take a look at one more example. Put this one. Log base 9. Let me write that better. So log base 9 of 27 is equal to 3/2. Okay, same idea. So here's our equal. Our base is 9. That becomes our base. What the log is equal to is our exponent. So that's 3/2. And then what's left is the 27. And once again, if you also evaluate this, okay, if you remember how to do fractional exponents, you can do either numerator or denominator first. So the top number is your power. The bottom number is your root. So 9 to the 1/2 is the same as square root of 9, which is 3. And 3 cubed is 27. All right, wrap up then, let's do a few evaluations just to practice with this. Here we want to evaluate without a calculator, primarily just to kind of understand the okay, actually, scratch that. Take that back. Let's not do that because I realize I haven't given you those rules. That will be in another video. So actually, this kind of concludes. Make sure you can first make sure you can use your log on practice using your natural log and log button log base 10 on your calculator. I also mentioned I didn't mention to begin with what logs are useful for. So logarithmic functions are often useful when you have a scale that often goes over too many numbers where it would be really difficult to use them. So one example is if you heard of the Richter scale for earthquake magnitude, that's actually a logarithmic scale. So if you hear that an earthquake is a 5 on the Richter scale compared to a 6 on the Richter scale, a 6 then, those are log base 10, those are the exponents. So a 6 on the Richter scale is 10 times as powerful as a 5. And then a 7 would then be 10 times as powerful as a 6 or 100 times as powerful as a 5. So that's why you often hear if you have an earthquake that's maybe of a 3 or 4 on the Richter scale, often doesn't do much damage, maybe some very small damage. But when you get to 5, 6, or 7, it does a lot of damage because you're increasing by a power of 10 each time. And also the decibel system, the way we measure sound, is also a logarithmic scale because it turns out the human ear can actually detect a pretty wide intensity of sound. And so if we just used actual intensities, we'd have to do with really big numbers. It wouldn't be very helpful, so they use a logarithmic scale. So we learned so far today are the basic properties of logarithmic functions. We also learned how they're related to exponential functions, and we saw some basic features of their graphs. Thank you. Have a good day.